Hello.
Hey,
Hey, how are you doing?
I'm good. How are you?
I'm good.
Yeah, so heard a lot of good things about you. Got an MCAT coming up in 2 weeks, so I was just
Yep.
gonna hope to pick your brain a little bit.
Yeah, of course. So, what have you been doing? Like, how's your preparation been so far?
So in between classes and MCAT study, I mostly wake up around 5:30 a.m. I try to
That's
do
crazy.
about
That's really early.
six. You saw that?
That's pretty early. Okay.
Yeah, yeah. I'm an early bird. My MCAT's at 7:30, so I try to make sure I'm at least doing questions by 7:30 every day.
Yeah.
So that just becomes like an optimum time for me to do it at.
Yeah.
And I do about
Look at what
no
my mug
less than
says.
70 night out. I
Yeah.
do about no less than 60, 70 questions a day to 100
Yeah.
with primary focuses in chem phys
Yeah.
and the biology biochem because like I'm in a master's program right now. So their
Yeah.
main concern is making sure I got the science thing.
Of
But
course.
I don't want psych, social, and cars to fall as well.
Okay. Yeah. But how are psych social cars?
So lately on my practice test, psych social usually around a 125, 126.
Yeah.
And on my MCAT, I scored a 125 on it.
Yeah.
Cars, my last MCAT, I scored a 124 on it.
Mm-hmm.
And the practice test always fluctuates. It's never really consistent.
Which practice tests are these?
AAMC.
Okay. All right. So, how did you on? You said you took the MCAT before. What was the breakdown for that? Your score breakdown?
So my last score for
Mm-hmm.
the MCAT was a 123,
For
124.
CP 123,
Yeah, CP 123,
cars 124.
cars 124, Biochem 125, and then Psych Social 123.
Okay. So so you want, but you okay. So what do you want to like focus on? You said you. Oh wait, I wrote CD. It should be CP. All right. So you said you wanted to focus on CP and BB.
Yes.
And cars, you and P and psych soc, you're going to, kind of like try to do that on your
Um,
own.
the, the last Psych Social, because I took that MCAT multiple times. Psych Social before this last one, it was a 125. It
Yeah.
kind of dropped to 123 because
Forgot
I
some
don't
of the
know, I
material.
kind of just got like a little anxiety and tired and it didn't go the way I
Yeah,
wanted to.
yeah,
But when it comes to the practice test, my Psych Social is consistently above 126.
yeah.
So I'm not too worried about Psych Social.
Okay. Yeah, psych soc is something that it's like predominantly content, so it's something that like you anyone can like kind of like raise their score without needing like any additional help. But if there are any topics, we can always go over any of those topics. Cars is usually like hard for a lot of people, um, but okay, let's just like like get right to it. So what do you have like any like questions or anything like any particular questions from like a practice test or anything that we can go over?
Um, I, so you have the AMC. Oh, actually, I can share my screen.
Yep.
There's this one question that was bothering me. So let me get.
Mm-hmm.
I'm trying to get better with my math. And one thing when it comes to chem phys,
Oh yeah.
I'm trying to get better with just looking at the units rather than memorizing equations. And
Yeah, if you don't remember a formula, you can deduce that from the units, and if you don't remember the units, you can deduce that from the formula.
exactly. So I'm trying to find this question. I think I flagged it.
Yeah, flagging is also very good.
Damn, where was this question? I've done so many questions that it's hard to find.
Mm-hmm. In the meantime, I'm gonna make a OneNote notebook for you.
Okay. Damn, that didn't fire.
Mm-hmm.
I'm gonna take no more than 2 more minutes trying to find it.
Yeah, if you see anything along the way that you don't, understand or need some clarification on, you can do those as well. All right, so I'm gonna share this notebook with you. I guess I should just use the email that.
Nah, use my.
Yeah.
I'm gonna put it
in the chat. Okay.
Right here.
So so your school is going to think that it's spam, so check your spam box. But I shared it with you now. But yeah, we don't have to look at it now, but
yeah, just got it.
Oh, cool.
I can't really find it, but something I've been having kind of trouble with is like kind of units and exponents when it comes to answering questions. Like, say I would have an answer that is 10 to the negative second. I was for some reason have 10 to the negative 5. It would be kind of confusing for me. So
all right. So start writing it this way. It's like a much easier way of writing it. Write it like a calculator would display it with that capital E.
Right as E.
Capital E. Like for instance, in your calculator, right? If you have something times 10 to the 12th power, it would just say 1 capital E 12.
Yeah.
So that way, it's much faster to write scientific notation. You don't have to write 1 times 10 to that exponent. Here, I'll share my screen and I'll show you some stuff.
Okay.
All right, you can see it?
Not yet.
Okay.
Not yet.
Okay, so here, same MCAT. So this is, for you. So basically here is some stuff with math that, okay, so for instance, all right, so logarithms, how are you with those?
I'm okay. It's just sometimes I'm not great.
All right, so I think it's always better or best to know why something is the way it is rather than just knowing that it is the way it is, because you can memorize something and that's whatever maintenance rehearsal in psych soc, but elaborative rehearsal is really getting a rich deep understanding of it. So essentially logarithms are essentially just the inverse of an exponent.
Okay.
All right, so here are exponent rules. So if you have x to the a power times x to the b power, what do you do to the exponents? You just add the exponents.
Yes.
You could see this, right? Do we need to zoom in or something?
Yeah, I'm good.
Okay. Now, if you divide things with exponents, you subtract the exponents.
Mm-hmm.
So if it's x to the a power divided by x to the b power, your answer is going to be x to the power of a minus b. Make sense?
Yes.
All right. Now, so like multiplication of exponents is addition, subtraction. I mean, and division. Sorry. Multiplication of things with exponents is adding. Division of exponents is subtracting. And now, if you take an exponent to the power of another exponent, that's when you multiply them. So
Okay.
if we have x to the a power, and we take that value in parentheses, and we take that to the b power, it's the same as x to the a times b power.
Got it.
All right. So for logarithms, it's the same principle. So if you have log of x times y, the answer would be log of x plus log of y. Right? And log of x divided by y, that's going to be subtraction. Log of x minus log of y.
Okay.
And then if you have log of x to the y power, you multiply them. So you have y times log of x.
Oh, okay.
All right. Now, if you ever like really forget, so like I use like red to like kind of indicate like really like, important stuff. So if you ever forget, remember that like this kind of like arrow thing, like that's kind of like what helps me kind of remember. So logarithms have a base of 10. They don't write that down, but it's just a given. So I wrote it down in this case, so you see that little 10 down there. Do you see that?
Yeah, I do.
Okay, yeah. So let's say it's the log x is equal to y, right? So how do we solve that? So I draw like an arrow from the 10 circling around the y and going back to the x. So that means that 10 to the y power is equal to x.
Oh, okay.
And that is true. So, for example, right, if you have log of 1, right? Ask yourself 10 to what power is equal to 1? And that's going to be 0. 10 to the 0 power is equal to 1. Pretty much anything to the 0 power is equal to 1, by the way. So log of 1 is equal to 0, okay?
Okay.
All right, now I wrote here log has a base 10, but sometimes you'll see something like ln, which is a natural log.
Yeah.
And that just means it's a log that has a base instead of 10, it has little e. And that's Euler's number. And I can talk like hours about Euler's number, but I won't. But it's like a transcendental number that like, kind of like pi or like the Fibonacci sequence. So if, the base was little e, which is Euler's number, it would be just natural log. All right.
Okay.
So you must be asking yourself, why even use logarithms, right?
Yeah, a little bit.
Okay. So like let's look at an example for like loudness, how loud something is. So here we have just a linear graph where we plot intensity of the sound as the y-axis. And on the x-axis, it's perceived loudness. So like how loud it appears to us, like through our ears. And what happens here is that, it's like basically nothing because we can't really hear. And then, like, we can't really hear, like, when it's, like, that low. And then, at this point, it shoots up. So so essentially, this intensity shoots up over here. So I wrote in red this range. So there's a small, narrow range where in green, right, there's a huge variation. Okay? So if there's a small range where it changes tremendously, it's hard to like, it's hard to like use that information in a way that is useful, because it just changes too fast and in too short of a range. So that's if we plotted it linearly. But if we plotted the log of it, right, we have a logarithmic graph here, then it's just a straight line.
Okay, I see what happened there.
Yeah. So I wrote, we use logs to describe numbers that vary by large amounts in a small range. So I said, remember when I said logs are the inverse of exponents? This is what I mean. I don't have to really go over that, but in other words, it's just a way to take real life data that's a curve and to make it a line, so it's easier for us to conceptualize. So, for instance, the increase of 1 log unit means that it's 10 times the original measurement.
Okay.
So, another example that you see that in is in like pH. Because if you have 10 times the amount of the H plus ion, the hydronium ion concentration, the pH goes up. Well, okay, it should actually technically go down because it's a negative log for pH. Yeah. But basically 1 pH unit is equivalent to like multiplying it by 10. Like multiplying the concentration by 10, right?
Yeah.
So basically that's logs, and these are things to memorize because and I also write them on like the scrap paper before like I would take the test, just because they come in like super handy. And also like I wrote them out in this way so things like multiple things equal the same thing, so you can like associate the things together in your brain, which makes it easier for you to remember it. Like, the more connections you have, the more you can remember it. So these are just, certain things to remember. Like for instance, like sine and cosine are going to be like sort of like inverses of each other, right? Like, like when sine is 0, it's equal to 0, right? And when cosine is 0, it's equal to 1. But when cosine is 90, it's equal to 0. So these things are all equivalent. So, you can take a look at this when you, take a look at your notebook. And I also recommend to use fractions whenever you can. Because the math with decimals is just stupid. It's just like, it's too much. And I think that, like, even if you there's the strategy of like rounding it. Like if you have something like, you can round something up and round something down and get like an approximation, but if you use fractions, then things end up canceling out. It's a lot more simpler. Like like an example would be, so okay, what would be the formula for the energy of a photon?
E equals hc over wavelength.
All right, now what's h?
You said what's h?
Yeah.
6.62 times 10 to the negative 34.
And what's c?
3 times 10 to the 8th.
Okay. Now, that's pretty annoying to do, right?
Very.
So, what if I told you that 6.626 is essentially just 20 over 3?
That makes it a little simpler.
A little, but check it out. The 3's then cancel out, right?
Oh, shit, yeah.
Yeah.
I should realize that.
Yep.
Yeah, so like, what, 20 times 10 to the 8th?
Yep. Yeah, so it'll be like, I think like 20 e, and like I get into the habit of saying e, like 20 e, I think like negative 26 or something like that. But yeah, fractions are super helpful. there's so many like questions that I saw that like at least for like next step, I think they like give you the rating of the difficulty levels of the questions, and they were a lot less difficult when I did it like my here, let me see if I can yeah, so for instance, like this is a question from next step, right?
And that's good because like one of the major things I also wanted to like get across is that it's like that stoichiometry and unit stuff kind of throws me off all the time.
Oh yeah, stoichiometry is essentially just you know, the coefficients in a chemical reaction, and there has to be an equivalent amount of whichever substance on the reactant side and the product side.
Yeah.
Um, but so like here's an example of a question that was rated like brutal difficulty, and okay, so like let's just check it out. For instance, like it says, suppose that a moderately hard surface such as the hard packed Earth. Oh, and then also like the MCAT and pretty much all standardized tests, they are designed to like psych you out, because if you think about it, pre-med students are like the most hardworking, like thorough, like need to have an A, like, you know, types of students that exist. So how can you design a test that will make it like difficult for them to score well on? You take advantage, you exploit their natural tendency to be thorough and perfectionistic to psych them out and to make them feel like, oh man, I didn't like study enough, or I didn't learn enough content. But don't let that phase you. Like that's what they're designed. That's how they're designed. You know. Okay. So like a main thing to like be able to, main ability to be able to like have, I suppose, is being able to separate what matters from what doesn't matter. And like if you do it like long enough, like you'll instantly be able to see like how to answer something just from like a few words. Like and that goes for like passages. Like for a passage, like we can do that like after I show you this. Like yeah, like don't ever read the passage. Read the questions first and just take it question by question, because the passages, they're not meant to be they're not meant to be things that you learn from, because they're not from textbooks. Like they're from like research papers that have been published like in Nature and other types of like research publications. So they're really like niche, obscure, you know, cutting edge kind of research, and AKA like, you know, stuff that like, you know, research scientists are reading. So don't, yeah, it's supposed to be hard, the stuff, but look at the question, and then in the question stem there should be like a key word, and then I look for that key word in the passage, and then I go from there. And I'll show you that like, you know, right after this. So like here's the question, right? So like I brought that up because it has so much extraneous information, like moderately hard packed Earth, blah blah blah, right? But basically decelerate a person making a feet first landing to a stop in an average of 0.09 seconds. So what's the person's deceleration in terms of g, where 1 g is equal to, you know, this 9.8 thing when falling from a height of 2 meters. So okay, this is their explanation. It says, whoa, this is a fairly heavy question. It might be one to skip over, mark, and save for later. Blah, 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 blah. They use like this kinematics formula that I never use, and it's just a bunch of work, right? Yeah. So this is essentially, so many kinematics problems can be solved using conservation of energy. So what that means is, so energy is like, total energy is kinetic energy and potential energy, right? The sum of the two. Yeah. Okay. And so, you know, as something falls, right, one goes to the other. So basically, like I write kinetic energy as capital K and potential energy as capital U. So if you have initial kinetic energy plus initial potential energy, it should equal final kinetic energy plus final potential energy, right?
Yeah.
Now, if something just drops, so if I'm holding this thing up here, it has a certain energy, right? So, what's its kinetic energy?
0.
Okay, so it's all potential, right?
Yeah.
All right, now when I drop it and it hits like the ground or whatever, what would be its, or don't really think about it like right before it hits the ground is what I'm saying. So right before it hits the ground, its potential energy would be a 0, and its kinetic energy would be at a maximum, right?
Yes.
So that means that initial potential energy is equal to final kinetic energy. All right?
Yes.
So okay, what's the formula for kinetic energy?
Kinetic energy equals 1/2 mv squared.
All right, and what about potential, gravitational potential?
I don't remember that one.
You gotta know it. Try it though. Try it. Mess around with
UGH.
What's the U? What's the U?
Wait, no, get the U out. GH. Damn, I forgot it.
So think about those units, and think about which one you need. So, H is in meters, G is in meters per second squared. What are you missing there?
Grams?
Yeah, which is a measure of
mass.
Yeah.
So it's MGH?
Yes.
Oh.
Okay. So see, if you I didn't want to tell you, I wanted you to figure it out based on the units. So if you don't remember it, you can figure it out based on the units. All right. So okay, if we have basically no kinetic initial energy, so that means that 1/2 mv squared is equal to mgh, right? Now, if we're setting those equal to each other, what can we cross out? What can we cancel?
We can cancel out the m.
Yeah. And then just solve for v. Oh, yeah, don't worry about any of this stuff. Just, try it with the variables.
Oh, okay, you're saying like conceptually solve for v, not on this.
Yeah. Yeah, just with the variables.
Okay. So v so v equals the square root of 2gh.
Yep. And now it says that h is 2, right? In the question.
Yes.
And G is just basically 10, right?
Yeah.
Okay.
So that's 20 times 2, which is 40. So the square root of 40.
All right. What would that be close to?
Oh,
What's the closest?
6 times 6 equals 36. 7 times 7 equals 49. So it's between 6 and 7.
Yep.
So around 6.5. So it'd be C.
Yep. So it's that, right?
Oh. Okay.
See?
All right.
Now
all right, Mr. Shane. Okay.
Yeah. Now look at that. How you did that compared to this nonsense. Fairly heavy question. Skip over. VF squared is equal to VI squared plus 2AD.
That makes it so discouraging to learn it.
Yeah. So yeah, I have that over here, right? So, and by the way, that is useful to know because that's the complete conversion of, potential energy to kinetic energy. So V final is equal to radical 2GH. Yep. And also, there was one day I remember my friend who's a math major, he was telling me that it's impossible to find the perfect the root of number that isn't a perfect square. And I spent like an hour on a subway ride trying to figure it out, and I did. So this is, you don't have to know this, but this is how you do it. So like radical 36 is equal to 6. Radical 49 is equal to 7. I subtract 49 from 36, and I get 13. And then I subtract 40, which is what I'm trying to get, radical 40, from 36, and I get 4. So it's going to be 6 and 4/13.
Okay,
but anyway, yeah, you don't need to do that because the numbers won't be like that crazy. And also, like, I memorized 0.09 as 1/11. So, well, basically, like, they were asking for the acceleration. I forgot. So wait, I forgot that part because we solved for velocity, right? Which was like
Yes.
6 point something. So that's where you take the time, which is 0.09 seconds, and whatever you get for your answer for velocity, you divide it by the 0.09, and then you get your answer. So I forgot that part. So my bad.
Okay, that's fine.
The answer you got happens to be coincidentally like close to the right answer, but remember that that's just the velocity, and they're asking for acceleration. So there's that step.
Oh.
So I think they want you to make this like 0.1 or something, but I mean, I just know it's 1/11, so I multiply it by 11 and I basically get 7g. Make sense?
Yeah.
I think I used it for this one too. Oh no, this one is even easier. So like, here's another one, right? And see, difficulty brutal. So a 40-kilogram child is accidentally pushed directly forward off of a ledge, causing him to fall and hit the ground at a 60-degree angle. If the child has 720 joules of kinetic energy at the instant before impact, at what velocity was he pushed? Assume negligible air resistance. So, yeah, I don't know why they're saying it's brutal, but basically it's just, you just put in the kinetic energy formula or equation. So, yeah, forget this one. Okay, anyway, let's do some problems from your test.
Okay.
Or whichever problems you want to do. It could be like from any of the tests. It could be like from the section bank.
Yeah. Well, this Chem Phys went kind of good. I got a 129 on it.
Nice.
I already kind of reviewed it. So I'm gonna go to this one. This one, I remember.
Mm-hmm.
I went through this one kind of when I was sick. I did this when I was sick and bad. I just really didn't care. I was already tired. So 124 on it. Can you see?
Yeah. Okay. Which atom is the site of covalent attachment of AMC to the model Tetra Peptide used in the studies? All right. My guess is that Tetra Peptide is just 4 peptides, or 4 amino acids that are bound together through peptide bonds, right?
Yes.
And yeah, tell me about a peptide bond.
Peptide bond, that's the bonds that bind amino acids together. That's the carboxylic terminus binding to the amino terminus.
Mm-hmm. Yeah, and there's gonna be some like resonance there, where the double bond on the carbonyl group can go and make a double bond with that carbon and that nitrogen.
Yeah.
So that's why it's like, pretty stable. And, planar in terms of like, flat. So yeah, I think you know how this would work, right? Because it's going to attach to it's going to make a peptide bond, right?
Yeah. Let me go for this one. I think
Mm-hmm.
this is one of the ones I already kind of did. Let's see.
Oh wait, we could go over that one.
Okay.
Because I remember going over this with your friends actually. So something to know about fluorescence. A couple of things, okay? Because there's a lot of questions about this. So okay, two things, right? So one. So all right, let's say you have like an atom, right? An atom, and it has like an electron in its ground state, right?
Okay.
So when an electron is in its ground state, it has less energy, right?
Yes.
And less energy means more stable.
Yeah.
Okay. Now, so like in what quantum mechanics is about is just that there's discrete like unit measurements like stepwise for something to happen. So like let's say it takes like 13.6 like whatever electron volts to cause a electron to go from its ground state to its excited state, right?
Yeah.
Well, so what number did I say? 13.6. So okay.
Yeah.
If you shoot it with something that has an energy of 13.5, it's not going to do anything.
Okay.
So it has to be specifically that amount. So let's say you shoot that specific and a photon with 13.6 electron volts at an atom. Its electron, so it's going to absorb it, and it's going to hold that energy. Because remember, energy is just it's never destroyed or created. It's always conserved or whatever. It's always conserved, transferred. So that atom's going to hold that energy, and it's going to make the electron go from its ground state to its excited state. Right?
Okay.
Now, eventually, when it relaxes back to its ground state, it's going to give off that energy, right? So it's going to shoot out a photon at the same energy level.
Yes.
Okay. Now, that's just how, it works. However, kind of like with resonance stabilization, if you have a conjugated double bond system, which means that there's a double bond, single bond, double bond. So basically a single bond between two double bonds. That's what conjugated means. That means that there's a lot of resonance stabilization there, right?
Yeah.
And remember what I said, stable, if something is a high energy level, it's less stable and vice versa. Right?
Yes.
Okay, so if something has a lot of conjugated pi double bonds, it's going to be very, very stabilized and therefore at a lower energy. So
more double bonds means it's gonna be more stable and have lower energy.
Yeah, conjugated double bonds.
Conjugated double bonds.
Yeah. So that's how. So like, if you ever look at a pigment, like if you just like Google image search like a pigment or something like chlorophyll or melanin or something like that, it's gonna have lots of those conjugated pi double bonds. So what that means is that it's going to absorb that specific energy level photon, and it's going to be excited, but unlike a regular atom, it's so well stabilized that it's going to be excited, but at like it'll still go up in terms of energy level, but not at the same energy level. It'll go up and go down a little bit.
Okay.
So that means that so when it eventually relaxes again, it's going to shoot a photon out that is going to be at a lower energy level than the photon that you shoot at it.
So the photon that shot out is going to be at a lower energy level.
Yeah.
Okay.
So, because otherwise, energy should be conserved. It should be the exact amount. So, the reason that it isn't the exact amount is that it can be stabilized. Like, just do like a Google image search for like melanin. So yeah, you see it?
Yeah.
Do you see it? So there's a ton of conjugated pi double bonds. You see it, right?
Yeah.
Show me like a double bond and a single bond and then a double bond. Yep. There's so many, right?
Yeah. Got it.
Yeah.
Okay, I see what you're saying.
The other images are funny. But yeah. So that's essentially why, like, so like I guess like certain people, like white people, I guess they don't have the melanin, so they get like sunburned and damage from the UV light. But if you have melanin, it can take that UV light, absorb it, and it's going to not like damage it. I have like these eye drops over here that are this color because they have vitamin B12 in it. And if you do the same thing by looking up, the structure of B12, which is cyanocobalamin, it's going to look similar. It's going to have a ton of conjugated pi double bonds. So anyway, so to relate it back to this is talking about like a chromophore or something, right?
Yeah.
Like if you like scroll up a bit. So okay, right here, I see. So and also this is what I do like with my students to like make sure that you can spot things, that you can like read with your eyes and see things with your eyes without having to like read it. So like show me where it says fluorescence.
Versus fluorescence? Fluorescence?
Yeah, that's fluorescent. What about yeah, good. So you see that emission is at 440 nanometers and excitation is at 360.
Yeah.
So which one?
Oh, so that would be the difference in energy.
Yeah. Which one is the higher energy one?
The 360.
Yeah. Good. Yep. So basically, yeah, they shot a 360 nanometer whatever laser or something at it, light at it, and look at what it looks like. Do you see all those conjugated pi double bonds in?
Yes.
So that basically made it more stabilized, and then it shoots out something that's at a lower energy. So yeah. So to answer that question, you're dividing it by, because they're saying that how much of the energy was converted into other forms. So it's just the difference between the two.
Yeah, and it's the only answer that's like taking a difference anyway.
Yeah, it looks kind of confusing, but like that when you divide something, it's the same as multiplying it by its reciprocal.
Yeah.
Okay. So yeah, this one may make sense.
Yeah, it does.
Yeah, there's so many questions on this type of stuff on the MCAT, like photons and energy and stuff like that.
I missed this one. What was this one? I'll put this one.
Let's see. Compared to the concentration of the proteasome, the concentration of the substrate is larger by what factor? Okay.
I think I remember going through this one. I don't.
Okay.
Let me go to the one that I actually chose this.
Oh, and that's like a good thing to like know or memorize, because I see that asked, like, the relationship between catalytic turnover and like Vmax and stuff.
Yeah.
Because I saw a question asking about the catalytic efficiency.
Yeah, that's like yeah.
Yeah, that would be kcat over km. Let's see. Concentration of enzyme for each experiment was 5 micromolar. What is kcat for the reaction at pH 4.5 with no chloride added? So okay, like, I would look at that table, right?
Yeah.
Okay. So this is also a good opportunity to go over like how to read the data stuff.
Okay.
So like, I think of it like kind of like Sudoku, like a game of Sudoku kind of. So like, for compound 1, right? It's we keep the chloride concentration the same. Like, and we change the pH, and then we see like, how that changes, the rate, right? So
Yeah.
it seems like as if the pH, so for compound 1, if you raise the pH, the rate goes down, right? All right.
Yes.
Compound 3, when we raise the pH, it also goes down, right?
Same thing, yeah.
Now, for the last row where they have a chloride concentration, we would compare that with the row that has that same pH, right? So one thing changes. So that's basically saying that, the addition of chloride seems to also, reduce the rate. So that, was probably easy. But let's see. The concentration of enzyme for each experiment was 5. Okay. What is the kcat for the experiment? Okay, so compound 3, 4.5. They say it's 125 nanomolars per second, right?
Yes.
Okay. Then you can just divide that. Well, wait. That's going to be... Okay. Yeah, alright. You could just divide that. Well, okay, so I have to check out the units. So the units are going to be, with seconds as the denominator. So, oh yeah, you could just divide it then. The difference here is just that the rate is in nanomolars and the concentration that they give you is in micromolars.
Yeah.
So I would just write... Yeah, so this is how I would do this. I would write 125 E, capital E, -9.
Okay.
Divided by 5 E -6.
And then you get 25 E -3.
Yeah. And then that's the same thing as 2.5 E -2.
And that's how you get A.
Yeah.
And then you check your units because I guess seconds is on bottom, so
yeah,
that's
so
basically the inverse. Okay, inverse.
Yeah,
seconds.
so that's how I I knew whether to divide or subtract or multiply. I just looked at the units. There's no particular formula or anything for this, and yeah, so made sense how we did that.
Yeah, it made sense.
Cool.
Oh
yeah. Oh yeah.
Data nuclei.
Yeah. So I remember, there's like a video where I was kind of going over test strategy and I was using this practice exam. And I clicked C at first and then I instantly changed it to D because the first part is right, but yeah, it turns into the stuff that it turns into isn't really, radioactive. But yeah.
It isn't actually the original thing, and it's probably not radioactive.
Yeah, which is actually not completely true, but for the MCAT, whatever. It's whatever. It's true.
Gotcha.
Oh, this is exactly what we talked about. So another way of talking about conjugated pi double bonds is if it's aromatic.
Yeah.
Yeah.
So aromatic stuff usually have a lot of double bonds in it, or it's like
conjugated double bonds. Yeah.
Conjugated double bonds.
Mm-hmm.
What's the difference between a regular double bond and a conjugated double bond? Yeah.
Oh, just if it's conjugated, then there's a single bond between the two.
Okay.
So think about benzene, right?
Yeah.
So there's a single bond between each double bond, right?
Mm-hmm.
So that means that you can draw an arrow from each double bond to the single bond. So that double bond changes and moves over to the next position.
Okay.
So that's where there's resonance.
Got it.
Yeah.
So, just writing that down real quick.
So yeah, that just went over exactly what we were talking about.
It's a gamma phosphate.
Yeah, let's see. Let me see that question again.
Question?
Yeah. What type of P32 labeled ATP? Okay, so I'm gonna look for P32 in the passage. I see it. Do you?
Not yet.
Okay. But yeah. Yeah.
See it.
All right. See? Now that's saying that. And then you see how afterwards it says radioactivity?
Yeah.
Was measured.
Oh.
Yeah.
Every time I think radioactive, I should think gamma.
That's the worst. That's like, the worst type of radioactivity.
That would make sense.
There's like an
I think I chose beta because I just saw like beta decay, and that's the MCAT just throwing that little trick at me. I think.
Well, yeah, there's tons of different types of radioactive activity. There's alpha decay. There's positron emission. There's electron capture. There's beta minus decay. There's gamma emission.
Okay, now I got it.
All right, so yeah, they said beta decay, right?
Mm-hmm.
So that means that it breaks apart and forms the gives off the beta, right?
Yeah.
So it would have to start off with something else. Oh wait, no. This is a different type. Okay. This is a different type of question. All right, let me look at that top part again. This isn't this is different. Okay. So, let's see. It has to do with where it's located. Oh, I get it. So, it has to do with where it's located, right? So, this is true for any type of like kinase, like a kinase that takes like a phosphate from ATP and puts it onto something. So they're saying that they labeled the phosphate from ATP that is added to the peptide or whatever, right? So which of the phosphates is it, right? Because adenosine triphosphate has 3 of them, right?
Yes.
So the one that's closest to the adenosine is the alpha.
The one over is the beta, and the third one's the gamma.
Yeah.
Okay.
So that's so yeah, you can kind of see how they make the test, right? They see like that information about the beta decay. They want you to look at that and then choose the beta phosphate as your answer.
Oh goodness, it's childish.
Because think about it. Like they can't make it like outlandish. Every choice outlandish. They have to make every choice plausible, or else everyone would get a perfect score. So, that kind of like, if you get into the mind of the maker of the test, you can kind of see like, oh, I see what you were trying to get me to do there. Because when I saw that, that's what I looked at first too. I looked for the radioactive decay. And then when you scroll down, I saw the answer and it wasn't beta. And then I was like, oh, hold on.
Makes sense.
Yeah.
Okay, I got it.
Okay, so this seems like it'll be something with the that table.
I ruled out D too, so.
What's up?
I ruled D out. I struck it out. So I'm thinking like, why'd I do that?
So, Okay, let me see like the chart or the table. They're saying that okay. Oh wait, maybe wait. So SPHM. So they're using something in place of that. Okay, got it. It's FLGFTY, right?
Yes.
Okay. Um. So. Okay. So let's see. We have for A we have alanine. For B we have glutamine. For C we have I forgot what
Glycine.
G was glycine. And for D we have glutamic acid.
Yeah.
Okay. Now alanine and so tyrosine. All right, so like there's a couple of ways to go about any type of question. Like if you don't know anything about it, you can separate what's different.
Yeah.
And then so let's try that. So alanine is pretty it's just a small useless amino acid. Glycine is like even smaller. All right, then we have glutamine, but the glutamic acid is like it's actually like an acid that actually like does stuff. So, but tyrosine is not. Wait, tyrosine. Wait, T is. Oh wait, is T threonine? It's threonine. Okay, never mind. So threonine, which is basically
It has a hydroxide group, and that could be protonated or deprotonated. Deprotonated?
So like also this is useful to note. STY, which is serine, threonine, and tyrosine. What do they all have in common?
So STY, they all have a hydroxide group.
Yeah. So those are the ones that get that kinases phosphorylate.
You said STY, right?
Yeah.
What's the Y stand for? The Y tyrosine?
Yeah. Because OH groups, because they're strong nucleophiles, they nucleophilically attack the phosphate and break the phosphodiester bond of the gamma phosphate of the ATP.
Yeah.
All right, so threonine. Yeah, why is it like glutamic acid? Like, it's the only one that's different, and glutamic acid has an OH group. That's what I think. Let's see. All right, what are the choices?
It's saying PDK1 dependent phosphorylate. Well, I don't know. I'm not sure.
Yeah. So let's check out the. All right, let me see the solution. Maybe that. All right. Phosphorylated threonine would most likely be mimicked by glutamic acid in terms of size and charge. Oh, okay. Wait. Okay. Oh, yeah. All right. When serine is phosphorylated, it gets negative.
Okay.
Like a phosphate group is always negative. And
so that would be true for that.
Yeah, acidic.
Tyrosine.
Yeah.
Or threonine.
Glutamic acid.
Yes.
So glutamic acid, like the acidic amino acids get turned negative, right?
Yeah.
So that's why they'll be basically, it'll basically give you the same experimental results because the phosphorylated serine is negative, or the phosphorylated threonine is negatively charged, and a glutamic acid is negatively charged.
Okay.
So
I could have thought about that in terms of that amino acid that they were given.
Yeah.
So that was
So
threonine, and the threonine has the potential to have a negative charge. Or I could have
yeah,
just
by
looked at
phosphorylating it. Yeah.
yeah, or I could have just looked at A through C and realized that
They're on.
those amino
Oh.
acids are kind of the useless ones.
Yeah, yeah, yeah. That's how I think of them too. AKA neutral, you know.
Okay. I was just reading the graph. I remember this one.
What's up?
Uh, but I was talking about this one. I already know. Like,
Mm-hmm. Oh, okay. Based on the data presented in figures 2 and 3, what's the most likely role of Y229 in protein stability and camp activation? So that's whatever, tyrosine, right?
yeah.
And so we got to take a look at figures 2 and 3. So figure 2, let's see. Activation of wild type and variant. Okay, and then those things show the same thing as... So Y229 is the same as wild type, essentially. So that seems to be, you know, the leftmost of the curves, which essentially means that it takes less, or rather, like, wait. So it means that it requires less camp, I suppose, to be activated. And then the thermal denaturation profiles, Y229A, that like gray dotted line. It's like the leftmost as well. It's kind of like the R241A1. So that means that it doesn't take much temp, like it doesn't need to be that hot for it to denature and unfold.
Yeah.
And that kind of makes sense because, you know, it's big. Tyrosine, you know, it has that, like, whatever. The, you know, the phenyl group with an OH to it. So, okay. So, let me see the question then. What's the role in it? Okay, so check this out. So figure 2 showed that it was the same as the wild type, right?
Yes.
So basically it doesn't it doesn't have an effect on the camp stuff.
Yeah, it's showing that the other two do.
Yeah. And then figure 3 shows that it does have an effect on it getting denatured. Because we compare everything to the wild type, right?
Yeah.
So it has a tendency to denature, to unfold, right?
Yes.
So it's going to be important for protein stability, but not critical for camp activation.
Mm-hmm. I got that. Well, I'm about to go to my question banks, some recent stuff. Damn it, where's the user protocol?
All right. Oh, do you want to go through these or?
Hold on, let me read this one. Yeah, sure. Let's do this one.
Okay. Which reaction leads to the formation of DHB? Is DHB that thing? 2,5-dihydroxybenzoic acid? Yeah, okay. So, alright. What makes that? Alright. Benzoquinone, hydroquinone. So, dihydroxybenzoic acid. hydroquinone, benzoquinone. I think so I can see why you chose something with benzoquinone in it.
Yeah.
So I think that benzoquinone would just be like a benzene ring with two ketones attached to it, like with two like carbonyl, like double bonded O's to it.
Yeah.
And that important part of the name isn't there anymore once those get hydroxylated, like turning into OH groups.
Mm-hmm.
So, and I think that that's what hydroquinone would be. Like a benzene with the OH groups, like on opposite ends. Do you?
I'm kind of fun. I'm trying to picture it in my head.
Yeah. Okay. So, let's see. So okay, let's just picture like picture like a benzene ring with one end attached to like a double bonded oxygen, and then the opposite end another double bonded oxygen.
Yeah.
So okay, I think that would be benzoquinone because it has the benzene and the ketones for the own part, right?
Yeah.
Now, when you reduce that, you're going to get it turned into an OH. Those double bonded oxygens will turn into OH groups.
Okay.
So then you have a benzene with an OH group at one end and another OH group at the other end.
Okay.
So that, I think, is going to be the hydroquinone.
Oh, so that's called a hydroquinone, and then
Yeah. So I know, like, that...
this is the carboxylation.
Yeah.
Okay, now I see what you're talking about.
Yeah.
Okay, so you're basically saying like a...
Yeah, the benzo part, that's really important. I can see why you would choose that. And it
kind of disappears in like the intermediate.
Yeah. They should call it hydroxybenzoquinone, but they don't.
Alright, I got it. That makes sense. Okay, let me go to... Oh, let me check. Was this one I need to open? Hold on. Nah. Because a lot of these, like, I kind of fully got over myself, but I know there are a couple that I'm less like...
Yeah, so this one has to do with something called a work function.
Yeah.
So remember how I told you, shoot a photon at, with certain energy level at an atom, it'll make the electron go up or whatever to an excited state, right?
Mm-hmm.
So let's say it took 13.6 electron volts to get that electron to go from its ground state to an excited state. That is like the maximum amount that, like, the most outermost, like, shell.
Yeah.
And if you shoot it with energy that's more than that, it's already... So, okay. I talked to you about it going from ground state to excited state.
Yes.
Now, if there's a certain amount where it's going to be enough energy to not just be excited, but to be no longer bound to the atom. AKA, that is equivalent to the ionization energy, actually.
Okay.
So, ionization energy is the energy for it not to go from its ground state past its excited state to a state where it's no longer bound to the atom. So, it's just hanging out there. Now, if the energy is higher than that, then it's, instead of just hanging out there, it's going to be moving. So the kinetic energy of an electron is going to be the energy that you shoot at it with a photon, subtracted by something called a work function. It's usually like a Greek letter that's like a circle with a dash or a slash through it, and that's basically the ionization energy. So so that's why kinetic energy of an electron is equal to the energy of the photon minus the work function. Because if the energy that you shoot at it's equal to the work function, it's just going to make it unbound. If the energy you shoot at it is greater, then you're going to get a number that's greater than 0. So that's the kinetic energy.
Okay.
So do you see how it said work function of 3.4 electron volts?
Yeah.
That is the work function, okay? So we're going to essentially so our kinetic energy is going to be equal to energy of the photon, which is HF, minus work function, which is 3.4.
Oh.
Yeah. And if we look at this math over here, right, they're in a, what is this? Oh, okay. So yeah, we can do like whatever, HF. And when we multiply these, we add those exponents, so they're going to cancel. So you basically get 20, right?
Yeah, but then we got to subtract by the work function.
Exactly.
Okay, so I'm trying to understand this conceptually. So to get the kinetic energy of the photon, I'm multiplying H times F, but then where does the work function come into play? Like, when am I going to know to use the work function? Like, should I just if it's given?
If you're asked the kinetic energy of the electron, right?
Yeah.
Because a work function is essentially just the ionization energy. It's the energy required to make that electron no longer bound to the atom.
Okay.
So like, let's say like my apartment is the atom. And I don't know, like this is like the electron, and it's shot with, and the work function is the amount for it to be right outside of like on the threshold of my door.
Oh. So the work function is the thing that allows to be on the threshold of your door?
Yeah, like it's no longer bound. And then
so
any additional energy will make it leave completely.
Okay.
It all comes down back to conservation of energy. Like some of that, like that work function is the energy to get it away from that atom.
Yeah.
And then that extra energy is given to that electron. So that electron has that extra energy, and it's going to make it move.
Got it.
So this is and you're gonna see it. So they said photoelectric effect.
Yeah.
Yeah. Show me where it says that. Yeah. So photoelectric effect is basically discovered by, it was like Einstein's first Nobel Prize, I think in 1912. Like everyone knows him for like E equals MC squared, but that was like later. The photoelectric effect is basically finding the connection between like light and an electron. Essentially, what he did was he shot photons, he shot light at like a metal, like a sheet of metal, and he connected that sheet of metal with a wire to something, right? And
yeah.
And electricity is just flow of electrons, right? So he basically discovered by shooting, light at a sheet of metal that, let's say, that sheet of metal is connected by a wire to a light bulb, right?
Mm-hmm.
And if I shoot light at that sheet of metal and the light bulb turns on, that means that sheet of metal is losing electrons because they're going to the light bulb.
Okay.
So it's the connection of photons and light to actual electrons, which can, be, further expanded into electricity.
Okay, got it. Makes sense.
Yeah, so those are the contexts that you'll see that kind of thing being asked.
Okay.
Okay, let's see this one. Which extraction procedure will completely separate an amide from the byproduct of a reaction between an amine and XL carboxylic acid anhydride? Yeah, so I'm also going to share with you my Anki deck, because in that I talk about, or in that I have stuff regarding carboxylic acid derivatives and their stability and things like anhydrides and things like that, because I'm trying to remember what an amine and excess carboxylic anhydride would produce and how that would be different from an amide. I think an amide is the least or most. Here I have it. Rather, I found the card. So basically, carboxylic acid and amine creates an. Oh wait, it creates an amide. Separate an amide from. Oh wait, but there should be a byproduct. Carboxylic acid and... Oh, wait, no. Carboxylic acid anhydride. My bad. Let's see. Carboxylic acid... anhydride. Alright, I don't... So, okay, since I don't... So I'm going to just try... Since I don't remember, I'm going to try to, figure it out. Carboxylic anhydride. Okay, I think I know what it looks like. It'll be carboxylic acids on both sides, and then connected, to...
Yeah.
Like that, and then connected like that. Then amine, what would that do to it? Alright, whatever. Let's see. Add this to... Okay, so an anhydride... I'm trying to remember which one... I think anhydride is the most unstable. Amide is the least stable. Yeah. Unfortunately, this is one of the things that you have to know, I think. So, there's a... What was that? There's a... I think MCATreview.com... No, MCATreview.org.
No, it's all good. I'm kind of trying to figure out. I'm kind of figuring out how to get through it. I feel like using the NaOH would be kind of obvious to me. Mm-hmm. I didn't choose that in this, but looking back on it, I'm just like, okay, NaOH makes sense. I'm just looking at that second part.
Mm-hmm. Acid derivatives. Okay.
Well, sorry if I don't seem responsive. I just got out of class and my brain is a little fried still.
Oh, yeah. No. I wasn't seeing that as well, at all. I was just looking up. All right, I got it. So, okay. Wait. Threw it in the chat. So, acid chloride, whatever, reactivity of these. Acid chloride more so than anhydride, more so than esters, more so than amides. So amides are the most stable ones. And so okay, they said add a strong base to quench the unreacted anhydride. Okay, then add diethyl ether, which is non-polar, and separate the layers. The amide can be obtained from the ether layer by evaporating the solvent. So the amide, you're saying that, okay, then the amide must be, because that's saying that the amide would then be, because if the amide is in the ether layer, it would be nonpolar?
Yeah, we can just go through this one through like the next session. I don't want to spend too much time on it.
Okay, sure.
I'm trying to look for that one quote. Nah, wait, yeah, please explain this one to me. This thermodynamic control and the kinetic control, I'm kind of,
Uh-huh.
oh no.
So
I have it reversed and I still can't really comprehend why.
Okay. Let's see. Okay.
Here's the paragraph where it says.
Okay, so lysosomes
researchers-
generated from compound 2 gave similar results to that in figure 1, only at pH 8.5, at pH 10 or above, and 7 and below. The liposomes of compound 2 did not form. The researchers mixed liposomes of different sizes and observed that those formed from compound 1 were stable to mixing, but mixing those from compound 2 formed new liposomes with an average size expected for the effective final lipid. Okay, concentration. So they're basically talking about, So okay, a liposome is, so imagine like, oil in water, for instance. Or, right? It doesn't like dissolve in water, so it's going to be like, it'll be like, make like these like circle things like called liposomes.
Yeah.
And if you have lots, so it's kind of like, okay, so if you have lots of those little, okay, so all right, back to the circle in water, which is a a fat or something nonpolar that doesn't dissolve. Like, if you have like tinier drops, so like I'm gonna do this reverse by talking about like, what is it, bile? Like, you know how bile is like an emulsifier?
Yeah.
So like it basically, let's say like in the fat cell we have like a giant circle of like fat, and that gives it a certain surface area, right? For like this circle. And bile acts as an emulsifier, which basically breaks it apart into smaller circles, which increases the surface area of it, so it can be better broken down and stuff, right?
Yeah.
So why does it go like the reverse of that? Why does it go and make like larger, like little like circle things that blah blah blah, like go in together and make bigger ones? Why does that happen?
I'm not sure.
Think about like what about like, even if it wasn't like hydrophobic, like even water, right? A droplet of water is like what shape?
So like a sphere or like a circle.
Mm-hmm. Yeah.
So polarity.
Well, that's where it's a polar one, but that works with like oils too. A drop of oil, right?
Yeah.
So pretty much any liquid, right?
Yeah.
Like they all pretty much turn into spheres, right?
Yes.
And in 2 dimensions, a circle, right?
Yes.
So why do you think that is?
Because they're not interacting with its surroundings.
Yeah, and well, it's the most stable, and you know, it's the most stable and least energetically. It's like the most energetically favorable um, shape for it to be in. Like, I oftentimes think of like how something would behave in space, and things like kind of apply to that too. Like, why are planets the shapes that they are, right?
Yeah.
Because that's not even
Okay.
with liquids. That's with solids, right?
Yeah.
And then what about stars? That's with gases. They all
Okay.
they all want to conserve their energy, so they get together and they make a shape that's the most energetically favorable shape, which happens to be a sphere in 3 dimensions or a circle in 2 dimensions.
Okay. Yeah.
So, okay, they're saying that compound 2, right, when they had liposomes of different sizes, right, like something this big, this big, this big, this big, right,
Mm-hmm.
they basically formed a new liposome that had a size for that final lipid concentration. So they made a big lysosome. So that one, and so that's the most stable form that it can be in. And thermodynamics is all about essentially things in the universe wanting to be in a state in an energetically favorable state, aka the most stable state. So that big, kind of like, fat bubble or lipid bubble or whatever liposome is this most stable state that it can be in. That's why in our bodies we have to make bile to break that apart into smaller things, because everything in the universe naturally goes to its most stable state. So we need to make bile to break it apart. Because if it broke apart into smaller pieces naturally, then we wouldn't need something like bile to break it apart into little micelles and stuff, right?
Yeah.
Yeah. So compound 2 form new lysosomes with an average size expected for the effective final lipid concentration, right? So it's
Mm-hmm.
basically just going to make really big liposomes that are very energetically favorable. So that means that it's under thermodynamic control.
It's a compound one or compound two?
Oh, 2.
Two. Okay.
Because 2, yeah, because 2 just makes essentially like a big one that is the average size of that final concentration of lipid. Whereas compound 1 just have, liposomes of different sizes just hanging out.
Hmm. So since compound one has those liposomes with different sizes, and they're not clumping together, that means they're more under kinetic control.
Yeah. So generally speaking, kinetic control is like the thing that happens fastest, and this doesn't really talk about that. But since we know compound 2 is thermodynamic control, then the other one would have to be kinetic control. And I remember going over this one, and I drew some pictures, so I'm going to share my screen for a second and show you.
Okay.
All right, you see it?
Yeah, where do I begin? Top left?
Oh, so like this, I kind of went over like almost like a bunch of things, but like for instance here, right? So here's the example I was showing you. So like in our bodies, right? Like in our adipocytes and our fat cells, fat is like a big circle, right?
Yeah.
because that's the most energetically favorable state. And what bile does is it breaks it apart into these smaller fat bubbles, which are micelles, right?
Mm-hmm.
Remember, like micelles and bio and stuff?
Yeah.
Yes. So everything in the universe wants to be this. That's why we have to make things like bile to make it into this. So over here, compound 1, we have liposomes of different sizes, right?
Mm-hmm.
And we just threw them into some type of thing and they, whatever, mixed in there, right?
Yeah.
And then compound 2, we took a bunch of them and whatever, we threw them in. And they basically just made, bigger, you know, lysosomes instead of being like, mixed in these different, and rather than different sizes mixing in with the solvent, they didn't do that. They just basically made one new liposome or whatever that has, the same amount as the average between these different sized ones.
Oh, okay. All right. That's starting to
But yeah, so and so it would make sense that this would have a concentration equal to the final, because it's taking all of these and putting it into that, so it's going to have that concentration, that higher concentration, right?
Yeah.
Yep.
All right. Okay. I got that.
Yeah. And then this, I could just show you this because it's with that same passage, but it's kind of like obviously on the test you're not gonna have time, but before that, if you want to like if you need help like understanding what a passage is kind of saying, I take notes like this. So for the passage that you're looking at now, I wrote like effective pH. I use this proportionality symbol a lot. It just means that if one, this pH is proportional to no change. pH is proportional to the concentration of compound 1. Concentration, I always use those brackets. And then I forgot what D was, but if it's 1 over something, it's an inverse proportion. So I think that's diameter. So, because this is for the passage that you're looking at, so like diameter is inversely proportional to the elution volume. And, compound 2 is roughly equal to compound 1, only at pH of 8.5. And it's not equal at pH less than 7 or pH greater than 10. But yeah.
All right, got it.
Mm-hmm.
All right, that makes sense.
You want to do this one?
Yeah.
All right. What mass of compound 1, that's a molecular weight, is contained in the solution used to prepare lysosomes that elute at 20 milliliters by size excluding chromatography? So I think I'm going to have to look at that, that thing down there. Okay. Elution volume, okay. 20 mLs is 0.1 millimolar. Right? So yes. I would write 0.1 E negative 3 molar. And molar is just moles per liter, right?
Yes.
Okay. So I'm going to multiply that by 800 grams per mole, and the moles cancel. So that's, and then I'm going to have an answer that's in grams per liter. And then I multiply that by the 20 mLs, which is just 20 E neg 3. So essentially, you're going to just do like 0.1, which is 1 over 10, E neg 3 times 8 E neg, 8 E2 times 20 E neg 3.
Dang. See, that's what I'm trying to get to. I'm trying to get to that fast recognition.
Yeah. So like, for instance, so like all right, so like molarity. So yeah, that 0.1 I can write as 1 over 10. Right? E.
Yeah.
Yeah. E neg 3, and then times the what was it? Oh, the 800. I could just write 8E2, and then 20E neg 3. So I'll put the 10 into the 20 to get 2E neg 3, and then let's see, neg 3, neg 3, neg 6, E2 is E4, and then I get times 2. Wait. 16. I don't know. Did you write it out?
I write it out? Yeah, I did 0.1 E neg 3 times 800 grams, or 8 E neg 2. 8 E2 times 20 E neg 3. I don't think that would get you the answer.
All right. Let me try this out. What? All right. So let's see. 0.1 E neg 3. 8E2. 20E neg 3. Wait a second. What am I doing here? Oh, wait. Wait. Hold on. Okay. Oh. You know what? Hold on. It elutes at 20 ml. But it doesn't mean that if you scroll up, there must be something else. There it is. Lysosomes are synthesized from 1 ml of various concentrations of compound 1.
Oh, so that's going to make it 1 E neg 3.
Yeah.
That's going to be the last multiplier, not the 10.
Yeah.
And then that makes sense because that'll give you micrograms.
Yep. Yeah, I only saw that thing, so I thought that's how much of it was came out, but the liposome itself, like compound 1 was mixed into 1 ml of I'm sorry, 1 ml of compound 1 is the thing. It just happens to elute at 20. So yeah. That gives you the answer?
That would make sense to me.
Yep.
Which one do I want to go over? Sometimes I just skip it because I know, like, this one.
What is the value of Km in micromolar for the wild type enzyme? Okay. Yeah, so it's that thing up there. So that is like whatever, Michaelis Menten or whatever thing.
Yeah.
So yeah. So okay. If you don't remember, because like it should be like V max, that 1.732 should be the V max.
Oh no, I remember this. I remember this one. I just kind of chose wrong because I didn't like double check the graph because I know I found okay, so 1.5, so that's the maximum velocity. Half that is about 0.75, so this is 0.75. So you go over that, and that's where it intercepts. So that's going to be 1.31. I just put
Yep.
0.675 because I just usually assume 0.5 right.
Usually assume.
I mean, not usually assume, but I guess I just
Oh,
I guess I
okay.
just forgot about one. You know, it was just like it was a dumb error. It was just a dumb error.
Okay.
I know.
I
guess I
you're
thought
thinking
this.
you're thinking of the V or whatever.
I think I thought I replaced this 2 with a 1
Okay.
for like I just looked at
Yeah.
this and said, oh, this is 0.5, 0.675, you know.
Mm-hmm.
And in fact, this is 1 because it's going by 1, so that was just.
Mm-hmm.
It's fun. I know I missed that. Check this one.
Okay.
Yeah, let's go through this one.
All right. So let's see. We got the molar mass of NaCl. We have the liter of the PBS thing, and we just need to know whatever moles of the whatever PBS thing or whatever, if they have that. They said 10 micromolars. Oh wait, no, wait. Sorry, 0.1. PBS has 0.1 millimolars of NaCl. So okay, we're gonna do 0.1 E neg 3 times 58.5 times 100 E neg 6. .585 E neg 9 is the answer. So that's 585 nanograms.
This ENEX stuff.
What's up?
It's a simple concept, but it makes everything faster instead of 1 times 10 to the negative.
Yeah, here I can show you exactly. See if you let me share my screen for a sec.
I got you.
All right, do you see that?
Yeah.
All right, so, all right. First of all, do these numbers make sense?
Yes.
All right. So 0.1 is 1/10. So I basically just took this 0 out by dividing it by 10,
Mm-hmm.
and then I multiplied this by 10 to get 585.
Okay.
And then I added these to get neg 9.
Neg 9.
Yep.
Yeah, I think I just be overthinking stuff, honestly.
But yeah, if you do the math like that, then you'll be doing it super, super fast.
Makes sense. I know I got that wrong. Get this one wrong.
Okay. Let's see. What quantity of nag 3 was required to reach the equivalence point in the titration? Okay. What is it? This is nag 3 with hue alone left and hue in the presence of some other stuff. What's that molar ratio supposed to be? Wait. So, wait. Let's see, like, above that. So let's see. And the hue in the presence of... Okay, we're not going to use the one on the right because that's just nag. We're going to use nag 3. And the equivalence point is, you know, that part like in the middle of like that like sigmoidal, like when it goes like kind of like vertical.
Mm-hmm.
So that seems to be, it's like that like negative 500 whatever heat per injection or something like that. And that's like 1, a molar ratio of 1, it seems. So that I'm assuming the molar ratio means the moles of nag 3 are equal to the moles of hue. So now we just have to see, like, by scrolling up, how much that is. So, okay. So, let's see. Okay, the hue lysozyme 0.1. Oh, they use like different amounts. Okay. 0.1 and then 25 injections of this, which is 2.5 at 10 micromolars. Oh, wait. Sorry. Okay. So when they're equal, okay. Okay, each of the injections of nag3 is 10 microliters, right? So 10 microliters. So, all right, let's just I wonder if this is going to be like an excess amount of work or not, because equivalence point is when the moles are equivalent to each other. And I just want to see 25. Okay, hold on. $250. Wait, E neg 6. 1 E neg 3. 0.0. All right, I think what I'm doing is might be too long. Oh wait, hold on. I think I know. 1/10 divided by 1/2.5, which is 2/5. 1/25. Oh. Okay. Yeah, alright. That's what I was going to do. I thought it would be too much work. But basically, so, okay, equivalence point means, alright, so that's exactly, alright, so like, you see how when I looked at the graph, I saw that there's a 1:1 mole ratio, right?
Yeah.
And that's true for any equivalence point. It's when the moles of the titrant is equal to the moles of the analyte, or whichever thing is you're dropping into the other thing.
Mm-hmm.
And so the the solution thing, it was 1 ml of something with a concentration of 0.1 millimolars.
Yeah.
And, you know, molarity times volume gives you the number of moles.
Okay.
So, you know, the number of moles was 1e neg 7. Ah, yeah. All right. Okay, I should have just done it kept doing it that way. Oh wait. Sorry. So basically, you just do like molarity times volume.
Alright, well, yeah, that way to get you molarity times volume.
What's up?
Would that isolate? Oh, okay, yeah, you're right. Molarity times volume. Yeah, that'll get you just moles.
Yeah, that'll give you moles, and equivalence point is when the moles are going to be equal.
Mm-hmm.
So you don't even have to do the math for the stuff with nag3. You just have to do, 1 ml times 1 millimolar. I mean, sorry, 1 ml times 0.1 millimolar.
Oh, okay. And so yeah, since it's a 1-to-1 ratio, it's gonna give you that.
Yeah, because then however many moles of Hu there are will be the same amount of moles of nag3. And so,
Alright, that's cool.
yeah, and to do it quickly, it will be 1 e neg 3 times zero point 0.1 e neg 3. So it'll basically be like the ones kind of like whatever cancel. But yeah, you would just do that. Like one times.
And
so you'd get like. Yeah. Mm-hmm.
Real quick, do you have like a sheet of like just relationships that are most common in MCAT? Like how like, for example, power is gonna be what newtons times velocity, stuff of that nature.
Oh yeah, well, so like think of things in terms of ratios. Like power is a rate is a or a ratio, aka a rate. That's why they're called. The same thing essentially. So power is a rate of change of energy, and energy is equal to work. So it's a rate of change of work. Right?
Because those are the connections that I'm really trying to make.
Yeah. And if you break everything down to their SI units, you can also figure things out. Okay, so like work. What are the units of work?
Work is kg times m squared over s squared.
Wait. Say that again.
Wait, kg times m squared
Oh, I thought you were
over
okay. Kilogram. Yeah. Okay. Uh. So you're saying kilograms times what?
times mass squared. I mean,
Meters.
not mass, meter squared. I said mass, meters.
Meters squared per second squared, right?
Per second squared, yes.
All right. Now, okay. So wait. So let's go back a step. So what about so what's a Newton in a?
Newton is kg times m over s squared.
All right. So how do you get from that to work?
Multiplied by meters.
Okay. Good. Now, let's see. Okay. And so that's would be a joule, right?
Yes.
What about uh? Okay, and then what about what would a watt be?
A watt is joules per unit time or seconds.
Good. And I like that you said unit time. Um, so if because that means that I can ask you this question: what is kilowatt hour a measure of?
You said what?
Kilowatt hour.
Kilowatt power?
Oh, sorry, kilowatt hour.
Hour.
Yeah.
Like 1 hour?
Yeah, like if you look at like your energy bill, it's going to be measured in kilowatt hours.
So that is kind of like the same thing. It's just multiplied by 6. I mean, not 6 by a factor, like by E6, right?
Just think of it, unit of time, like you said, right?
Oh, yeah. Okay.
So kilowatt. So a watt is a unit of something over a unit of something.
Yes.
So what are those? What are those somethings?
Working time.
And now kilowatt hour
is just same thing.
Well, it has the watt part and the hour part. Kilowatt hour basically is multiplying it.
Not following.
So when I say kilowatt hour, think of the word kilowatt and a multiplication symbol and then hour.
Okay.
So what is that going to be? A unit of?
Oh, I see what you're trying to get at. It's just going to be joules.
So energy, right?
So energy.
Yep.
Oh, so you're trying to make me go back. Okay.
Mm-hmm.
I see what you're doing.
All right. So what is so liter is a measure of what?
Volume.
Okay. And volume. So okay, so like and distance. So okay, relate distance and volume.
Meters cubed.
Good. So now, what about pressure?
Pressure equals nRT divided by.
Oh, you're thinking of like
nRT per unit volume.
So that's why memorizing formulas don't work, because people, shove things in there, because that's only true for ideal gases. And
when they're negligible.
But think of it in terms of like in a pure physics, like how you were doing it before with like unit of this, unit of that.
Wait, what was the question?
Oh, for pressure.
So how do I get pressure? Pressure is volume per meter per something. I don't know.
If okay, so let's see. So if you have a really sharp knife and then you compare it to a blunt knife, what changes there? Oh, we're gonna have to go because I have another student now. But basically, pressure is basically a force over. It's like a unit of force over a unit of area.
Pressure is okay, that actually makes sense. Force over unit of area.
So think about like a blunt knife. It has more area, right?
Mm-hmm.
More surface area, so it's not going to be able to cut even if you apply that same force, because its pressure is going to be really low.
Okay.
And a sharp knife, and you apply the same pressure, it's sharp. So the area, cross-sectional area, is going to be a lot lower, so the pressure goes up. That's why it can cut.
Okay, that makes sense.
Yeah, and like a little like homework thing, think about what is this a unit of? I put it in the chat. Liters times ATM.
Liter times ATM. Thank you, Shane.
All right, hope this was helpful, and yeah, I'll like send you like and then check out that notebook, and we can talk through like text or like email about when we can meet next. Okay.
All right, sounds good.
All right, take care. Okay.
All right, you too. Bye.
All right, bye.